lobby right now. So I think we will start. So before I start, let me just talk about Dirac's like bracket notation. Okay, so like this is simply a notation invented for convenience of uh, like easy manipulation of expressions. Fine. So at the moment, it suffices to understand that whenever we pronounce a word like Ketsai, it would be written like the following thing, right? So Ketsai would be written within a forward angular bracket symbol, right? And that would be called as Ketsai. Fine. Similarly, the adjoint of Ketsai, like defined by the following result, would be called a bra of psi. Okay, and together, like that's why there is this name of bracket notation. So we will see how it really simplifies our way of writing things in due course of time. Alternate notations involve things like writing vectors as psi and psi twiddle, right? But then you can see you will have to use too many twiddles around. Yet another alternate is writing between circular uh, and a straight line. So this would be written like this. So that is like there are various notations by which people write it, and there could even be like notation like Esai and Esai dagger. So there are various types of notations which are used by people to represent these vectors in linear vector space. However, we will restrict ourselves to Dirac bracket notation. Fine, and as we have already discussed earlier, a linear vector space denoted by the script V, right, is a set of elements. We can just for notational purpose write these set of elements as V1, V2, Vk. It could be having a finite number of objects. It could have an infinite number of objects, right? So such a set script V can be told of as a or can be taken as a linear vector space, provided the following rules under operations of addition and multiplication are satisfied. So what are the rules under addition? So the first rule under addition is if v1 and v2 are contained in this vector space script v, then v1 plus v2 should be equal to v2 plus v1. So this in mathematical language is also known as commutative property, right? So the like these vectors are commutative under addition, operation of addition, fine. And the fact that if v1 and v2 are contained in v, then a sum of them will also contain in v is called the closure property. Okay, so for physics students in this batch, like if you hear mathematicians talk about commutative property or closure property, then this is what it means, right? So under addition, the fact that any two vectors added together is also a member of the same vector space is called closure property. And the fact that order of addition does not matter means that it is commutative under addition. Fair enough? Right. Similarly, now when we are writing this V1 plus V2 plus V3 equals V1 plus V2 plus V3. So the order of addition does not matter. Right. So like this, we can say associative or also like one can say, so what is difference between distributive property and associative property? What is difference between distributive property and associative property? So we'll soon see an
So
example where we'll come to it. Okay, so at the moment, like this is an associative law, right, or an associative property for the vector space. Now there exists a null vector which we will mark as ket null, which contains in V. So ket null also must contain in this vector space, such that if we are adding this ket null to any ket, that will leave the ket unchanged. So under addition, that is a special property. And similarly, there exists a unit vector which would be the additive inverse. So let's call it as additive inverse. Okay, so for every vk in V, in script V, there also exists a minus vk or minus ket vk, right? Such that when you add vk to minus ket vk, you arrive at a null ket. Okay, so here, as we like discussed earlier, we should not confuse ket 0 with null ket, because ket 0 has special meaning. So this ket 0 has a special significance. Right, and this typically has to do with, say, in quantum mechanics, it has to do with ground state. In quantum field theory, it has to do with the vacuum state, right? So vacuum really does not mean it is null. Okay, so this is a subtle point, but as we see examples, we would be able to make it more clear along this course. So furthermore, there is also this operation of multiplication, under which following properties must be satisfied if we say script V to be a linear vector space. So the first property is this property of like scaling. So if you have a number or a kind of we can call it a scalar, which is either a real number or a complex number. So then if you multiply a given ket vk by that number, so that product would still remain in the vector space script V. Okay, so that is very important. So this is basically telling us that there is a scaling. So the ket vk is scaled by factor a, and a need not be pure real, a can also be complex. So we'll come across examples later on where this complex a's have a significance, physical significance. So similarly, a times b times vk can also be written as ab times ket vk. So that's another property which has to be satisfied. So whether you scale it first by b and then by a, like overall the scaling is as if it is scaled by a product of a and b. So that's another property. And similarly, under like multiplication of a to a sum of kets. So suppose we have a ket vj plus ket vk, and then like you scale it with a, then that is equivalent to scaling these individual vectors by a and then adding them together. Okay, so in that situation also, if the final vector contains in, so this again contains in V. So this is crucial. Okay. And then besides that, you will have a plus b of vk would also be written as, so if you are if you can partition the scaling factor into two parts, and then like scale the particular vector by the sum of these two partitioned quantities, then that is equivalent to individual partitions scaling these vectors and those two vectors, resultant vectors, being added. And finally, we have an identity element. So one would be the identity, like, so it's like if you multiply, or rather I would not use the word identity here. So if you multiply a vk or scale a vk by 1, so that leads to vk itself, and if you scale vk with 0, then that leads to a 0. So by the way, here 0 can be used to denote both the number 0 as well as ket null. Okay, so in many expressions you see on right hand side, like later on we will see, on right hand side there would be a 0. So you can also assume it to be a null ket, and it would become much more clearer based on the context. So now with this, there is an additional idea which one has to be, and that is to understand the dual of a vector space, of a linear vector space. Okay, so this is again very crucial. So how do we define dual of a linear vector space? So we can define, say, every or all, let's use a better notation. So there exists script V for all V. Fine. So such that if V1, Vk contains in V, then V1,
Hello,
Vk
sir.
contains in.
Hello.
Yes, 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 please
Yes,
tell me.
sir. Maybe there are someone in the lobby. Please.
Oh, I see. Is it? Okay, thank you. Thank you for letting me know. Maybe they joined late. So admit all. I hope that it does not really disturbs our. So Raj Das and Mukesh. So let me just make sure that they also become attendees, because otherwise we will have an issue. Okay. Okay, so I think they have joined. Now let's start. So, like we were talking about dual of a linear vector space. So the proposition was that corresponding to every script V, where script V represents a linear vector space, there exists a tilde script V. Okay, and if that is the case, then if V1, V2, Vk are contained in script V, then their adjoints, that is, if ket V1, ket V2 up to ket Vk and so on contains in script V, then bra V1, bra v2 up to bra vk and so on is contained in script v tilde. So in that situation, we call as dual of v, right? And this also implies that v is dual of script v. So the behavior is mutual, and also so if you are applying these two duals on script v, then that would be equal to kind of v. So it is important to keep in mind realistic examples, okay, such that you can think of the connection between the uh, vector space and the dual space. So suppose let so another notation of writing this, so this can be, say, one way of saying it would be, say, suppose this is some ket vk, right? So if this column vector is contained in script v, that is the linear vector space, then 0 1 3 4 1 is contained in v tilde, and accordingly, like this we can call as ket vk, and this is the corresponding bra vk. Okay, so you can imagine this to be a 1 by 5, maybe 1 times 1 row, 1 column, right? 1 column and 5 rows. So it is an n cross, so let's call it 5 cross 1 column vector. Then this is a 1 cross 5 row vector. Although most of these things will sound trivial in the beginning, but understanding this language, the way it is spoken, is important or is crucial if you want to make like further progress in this domain. Okay, so now let's talk about, so whenever there are these two these kind of vectors, like the next thing that one needs to understand is the idea of inner product of two vectors. Okay, so if we are like calling these vectors as, say, let's just define some of the vectors v1, v2, v3, vk contains in script v, and let a, b, c, whether we will use it or not, let's see, but we'll write it down. I think it would be enough to talk of two variables, two constants here. So let a, b is contained in complex number set. It could also have been a real number, right? But at the moment, we'll consider a more general case where A and B are in complex number case set. So the general properties of inner product are as follows. So suppose we are doing an inner product of say V1 plus V2 with V3. Okay, then the notation is this would be equal to V3 V1 and V3 V2. So this is kind of crucial. And similarly, like there is a commutation kind of a property or commutativity kind of a property where one can take this V1 plus V2 and one can take a dot product with V3, and in that situation this is going to be V1 V3 plus V2 V3. So this is another property. A third property which is crucial is to consider a kind of dot product of V2 with a vector V1 but scaled by an amount A. So suppose I am scaling a vector V1 with A and then write it as V2, then like a dot product of this quantity, then this could simply be written as A of V2 V1. However, like why this has been written because of the fact that suppose we are multiplying say V2 on which A has acted, right, and then take a dot product with V1. Then in this case, if you try to bring out this A, this would be A star V2 V1. So this is crucial. And similarly, if we are taking V1 V2, then that would be same as V2 V1 star. So this is yet another property. So in particular, like you have to be careful about this complex conjugation part. So that is very crucial. Okay, so you can imagine like these vectors to be scaled by complex numbers, but when you are like acting it on A, okay, so here there is a catch, right? So we will have to see it has acted on V1 and then we are taking it through V2, so it is fine. And when we are taking it on V1, A V1, yeah, fine. So now the next quantity, like which is inner product of a vector with itself. Right, so that kind of defines, that helps us define something called the norm, and we will see why this is important because we will soon, towards the end of this class, we will know how to use Gram-Schmidt orthogonalization process to find an orthonormal basis for a given vector space. Okay, so that's an interesting problem which needs to be like whose logic has to be clear, and although like this is something which is taught in undergraduate and postgraduate classes, but I have come across PhD students who cannot do this Gram-Schmidt orthogonalization. And then when you go to that, then you will have to go back to the definitions of duals and then go back to the basic definitions of linear vector space. So therefore, when I am teaching linear algebra, I am not presuming any of these ideas. So norm of, say, when we are saying it is important to talk of norms, so suppose we are talking about norm of ket psi, and that is equivalent to, in notation wise it is written like this, and that would be equal to the dot product of psi with itself, and you take the positive square root. So the norm of vector is a positive number and it vanishes. So this is a positive quantity and vanishes if and only if ket psi is equals to null ket. Okay, so that's important. So therefore, that's how you are going to define norm given vector. So let's just take quickly a simple example. So suppose we are taking a vector like, say, let v5 equals to maybe 1 1 minus 1 1 0, some vector v5, then norm of v5 is going to be how much? It's going to be root under of 1 square plus 1 square plus minus 1 square plus 1 square plus 0 square. So that is root under of 4, and because we are taking the positive number, so it would be 2. So that's how norms are obtained. So now
Sir,
we will come to this idea of, yes, please.
sir, what in linear algebra we have done that inner product of two vector is always greater than equal to 0. But here we have
Yeah,
not defined such property that inner product of two vectors is greater than equal to 0.
right. So I have just told it that norm of psi is going to be a positive quantity, and put an additional caveat that like this quantity is going to vanish if and only if ket psi is a null vector. So essentially we are saying the same thing.
So what
Okay, so
I'm
when
saying that for any two vectors we have that inner product is greater than equal to 0. But here we have a positive quantity when we are taking the same vector. But
yeah,
positive,
okay,
uh,
okay.
but what
So yeah, agree, good. So we may come to that in due course of time when we are obtaining like some of the other results. As and when we will require it, we'll obtain that.
okay.
Yeah, okay. So at the moment, whatever rules are given, like using that, the same argument can be proved. Okay. So now let's just go to the next idea, which is again very crucial. See, these are like the problem of doing some of these things are in a typical class are that students have already seen it, but many a times there is a large percentage of class which has not really done it properly. So therefore, before we go to slightly more advanced stuff like singular value decomposition, right, which is something which is, if I say, crux of vector algebra, so one of the important thing is to understand how to do singular value decomposition. And it turns out like even our students at master's level, PhD level, or means around the world, students at these levels, like when they sit for typical interviews like Google or say Facebook, one of the very favorite questions as far as the technical part is concerned, because that tells whether the candidate has understood linear algebra properly. Fine. So in order, before we do that, at times it turns out that we have to backtrack a lot with typical students from Indian universities. So under such circumstances, it is a good idea to go through these preliminaries, and that's why like a typical evening class of this sort is really a good forum to go ahead with it, right? So we can do things at ease and slowly, without having a burden that okay, we are spending too much time on reasonably simple things. Okay, so this idea, the next idea which is crucial is to talk of basis set and an associated point related to dimensionality. So a basis set in a linear vector space is a set of vectors and call it Vk, and k equals to 1, 2, so on, such that the following two conditions are satisfied. So the first condition is they must be linearly independent of each other. So this simply means that no vector out of these VKs can be written down as a linear combination of other vectors in the same set, right? So that is one thing. And another way of representing it is if we sum over all k and write this as AKVK equals to 0. Fine. So this must have no solution other than the trivial solution that all the AKs are 0, right? So that is if and only if AK equals to 0 for all k, right? So if this condition is satisfied, that is another way of stating that each of these vectors v1, v2, up to vk and so on, they are linearly independent. So that's the first criteria that it must satisfy. And the second criteria is also called spanning the space. And this typically means that for every vector, like say for all vector, like say we can say psi contained in script v. So psi can be a typical vector. We don't know what kind of a combination it is, right? So for all psi k, we can write a thing like psi equals to sum over k vk vk. So these vk's are such that we can write any arbitrary psi as some kind of a sum of scaled vectors v1 to vk, scaled by different amounts. So here, in general, these ak's and vk's are contained in the set of complex numbers. So that is one thing, and the entire idea of span of a vector or a set of a vector is easily understood with a typical maybe three-dimensional like Euclidean space problem, or maybe like you can also try to kind of cook up special problems like to understand this. So for example, if you have to construct a vector, say so let's say example. So if we are talking of a vector a b c contained in a given linear vector space, say we call v3, right, then we automatically see that this abc could be written as a times 100 plus b times 010 plus c times 001. So therefore, like these set of vectors, which is 100, 010, and 001, forms a basis set. Fine. So here you have to understand that this is not unique. You can always cook up another set of three vectors which are linearly independent. So here you can see that like these three vectors which we marked, like suppose let's call them as maybe ket v1, ket v2, and ket v3. We can see that like if we are writing it as ak vk, a equals to 1 to 3 equals to 0 if and only if a1 equals to a2 equals to a3 equals to 0. Right, and I leave it as an exercise to show that you can always write another such set. Like for example, I could also have written say -100 as v1. That also is a typical vector in the given vector space. So even with -100, 010, and 001, we can span this. However, in that case, the new a1 would be equal to minus of a1 as used in this case, and which is a here. So the new a1 would be minus of a. Fine. So that way, like it is important to see that this is not unique. And then this idea of dimensionality. So the number of vectors that constitute the basis set is equal to the dimensionality of the linear vector space. So this is again crucial. Okay, so for example, every basis in a say p-dimensional linear vector space has exactly p vectors. Okay, and no collection of say q vectors in a p-dimensional linear vector space can be linearly independent. Okay, if this q is greater than p. Fine. And finally, no collection of say q vectors in a p-dimensional linear vector space can span the space if q is less than p. So these are kind of crucial, and a fundamental theorem that really simplifies the study of any given finite dimensional linear vector space can be stated as follows. So let's just write down this theorem. Of course, in physics, in a typical course like this with the given amount of stuff to be covered, we will be stating this theorem without proof, but I would kind of point you to where you can look up for proof. So every q dimensional, let's use p because all our initial definitions which I spoke out were p. Any p dimensional linear vector space okay, so here we can say this. We will restrict it to Euclidean space here. So every p-dimensional linear vector space is
Hello.
Hello.
Hello, sir.
Hello.
Yes, sir. Maybe Rashmi Ranjan may be in the lobby. Can you please?
Okay. Thank you. I'm sure Rashmi Ranjan is joined. I see. I hope we don't. Are we fine with? There are no changes as if the screen is still shared, right?
Yes, sir.
Right. Isomorphic to, let's use the Euclidean. Okay. So isomorphic to Rn, that is to the set of vectors.
So it should be RP.
Yeah.
P. Yeah. Sorry.
R.
Sorry. Sure. So everyone is awake. That's very good to see. And this would also be P, right? So sometimes we have to use this also to confirm how everyone is responding. Okay, so like I will come to this definition of isomorphic in a while. So what I was saying is every p-dimensional linear vector space is isomorphic to Rp, that is to the set of vectors in p-dimensional Euclidean space. So what would be a typical p-dimensional Euclidean space? Right. So here we have to understand that we can talk of this p-dimensional Euclidean space only when we assign a metric, right, to, so like we have to assign a metric to this before we can really call it a Euclidean space. So like this notion of metric has to be brought about. So what is metric? This is actually telling us how we measure distances in this space. So those of you who have done say plane coordinate geometry in +2, means those particularly I'm talking about physics students, then the conventional coordinate geometry that you would have come across, you can very well kind of start developing an intuition of Euclidean space based on that. So like for example, say in a typical two-dimensional Euclidean space, say x1 and x2, right? So if we are finding distance between two objects, like 2 points, right? So this may have a x1 1 and x1 2 if we are like trying to give some notation to this, and this is like x2 1 and x2 2, right? So then this length, which is the shortest distance between these 2 points, so although I may have given an impression that this is kind of a curved line, but let me tell you that this is a straight line, right? So you know that the distance is going to be, so suppose we are saying ds square is, ds is the distance, so ds square is going to be, so the difference between, so x22 minus x21, x12 minus x11 whole square plus x22 minus x21 whole square. So please understand that like the superscript here is just a number, so it's not square basically. So I think I have chosen a very bad notation here. So let me use a better notation just to make sure that there is no confusion. So x2, yeah, same way here. So let's call this point A and this point B. So then we can call it as x1b, x1a, and x2a, x2b. Then we can very easily get rid of this superscripts, which is not required here. Although eventually these are inevitable, these superscripts are inevitable when we are talking of tensors or tensorial quantities.
Sir, sorry to interrupt you, sir.
Yeah, please.
Sir,
Tell me.
sir, in equation in one's type, you have write the interval in a differential form, but in the
So that is
right side, you have not.
just because, okay, agreed. That is just because it's like that's how we write metric. So we can also consider a scenario where A and B are very close by. Okay.
Okay, sir. Okay, thank you,
Fine,
sir.
fine. So
Hmm.
A and B are close to each other. Agreed?
Yeah, agreed, sir. Thank you.
Raj, is that fine? Okay.
Yes, sir. Fine.
So therefore, like what I was saying was this notion of metric has to be associated before we can call it a Euclidean space. So that's a point which is required. So any particular, say when we are saying Euclidean space or later on Riemannian space or any other like given space. Like we need to associate a notion of metric. This will become more clear later on when we solve some typical physics problems. Okay, so now with this, I would like to just point to distinction between finite dimensional and infinite dimensional. Infinite dimensional linear vector space versus infinite dimensional linear vector space. So, like this has a finite basis set, right? And this does not have a finite basis set. We will see, although this like this idea of infinite dimensional linear vector space is difficult to digest initially, like how would we maybe talk about closure property, or how would we, if we don't know what is the basis set, how can we say that it is indeed linear vector space? Because in whatever we have done till now, a typical linear vector space could be talked of as, so in a single expression you can talk of as is for all v1 and v2 contained in v and a b contained in c, right? A v1 plus b v2 contains in v. So that is basically the definition of linear vector space. But when we are talking about, say, infinite basis set, or a situation where there is not a finite number of basis elements or basis members, then it's highly counterintuitive to think about these linear vector spaces. But that's where I think talking of a physics example would help. So to develop an intuition, a physics example will help. And what I would be doing is a 1D infinite potential well. What we are talking about is let's see if this entire thing can be here. What we are talking about is a particle in a in a 1D infinite potential well. So let's move this entire thing here. Just don't want it to be in the middle of the page. So like what is the problem? Let me just state. For students of physics, this is kind of very easy, right? However, for students of maths, we'll have to consider that that part, that they may not have been aware of this terminology. So we will have to introduce this problem properly. So we have divided this into region 1, region 2, and region 3, right? So basically this is a one-dimensional space, right? And we are talking about two locations A and B. So this can be written as a potential Vx equals to 0 for all x contained in 0 comma a and is equals to infinity otherwise. Okay, so we are basically talking about a kind of potential, and you can associate this potential with the idea of energy. So as if say the potential energy in region 1 is infinite, the potential energy in region 3 is infinite, like everywhere, and only in region 2 it is 0. So of course, like you will agree that if you are a happy particle, you would like to region, you would not be able to survive in region 1 because you need to acquire an infinite potential energy, and similarly in region 3 for the same reason. So here, like this problem is a problem like one of the basic problems in the quantum mechanics that undergraduate students of physics learn. But this connection to linear vector space, although it is very kind of profound and very useful at this stage, is not made very clear. So although like it's possible that some of the physics students would be aware of it, but I'm sure that a significant majority of students would not be aware of this connection to linear vector spaces. So the problem goes something like this. So there is a famous equation called Schrodinger equation, which states that we have a quantity called Hamiltonian, which acts on a like vector called psi, and it gives back psi with a factor in front. So here E is real, right? And H is an operator. Another version of writing the same equation is in terms of the coordinate representation, where this H would now be minus H cut square by 2m d2 dx2, where H cut is Planck's constant, m is mass of the particle, and this is how the kinetic energy part of Hamiltonian is written. And then there is a potential energy part, right? And in the in the coordinate representation, it is also useful to write this as h psi x equals to E psi x. Okay, so these are just two representations. When you are saying this one and this one, these are just two ways of writing, like two ways of expressing or two ways of writing the same thing, okay, or the same physics. So one where you are dealing with vectors, other where you are dealing with functions. So now, like given the problem, the simplicity of the problem here, we can see that in region 1, right, say suppose we are take this color. So in region 1, this psi 1 of x is 0 everywhere, because as per the postulate of quantum mechanics, psi x is the wave function corresponding to the particle, such that mod psi square is the, or modulo of psi square is the probability of finding the particle in that region. So because V is infinity here, so therefore straightforwardly mod psi1 square equals to mod psi2 square equals to 0. And that alternatively goes into mod psi1 square equals to mod psi3 square equals to 0. And that also means that mod psi1x equals to 0 and mod psi3x equals to 0, or psi1x equals to 0, or psi3x equals to 0. So only psi2x needs to be obtained, and for that in this region potential is 0. So therefore this equation simplifies. This equation takes the form minus h cut square by 2m d2 psi2 by dx2 plus v is 0 there, so that is equals to e of psi2. And that is a famous second order linear homogeneous differential equation, which we can write as where k square equals to 2me by h cut square. Okay, so all of us know that like this kind of a second order homogeneous linear differential equation have solutions which can be written down in a various ways, like in terms of the corresponding irreducibles. So one of the famous irreducible set is sin kx and cos kx. So therefore the psi2x could in general be written as a sin kx plus b cos kx. Okay, so here now we know that there has to be these boundary conditions. Arising from continuity of psi2 with psi1. So at x equals to 0, so there are two boundary conditions. At x equals to 0, psi1 0 equals to psi2 0, and at x equals to a, psi1 a equals to psi2, psi3, no, psi2a equals to psi3 of a. So let's write it neatly. So if we call this as boundary condition, say 1, and this as boundary condition 2. So 1 implies 0 equals to a sin 0. So that is a sin 0 plus b cos 0. That is b equals to 0 straight away, right? And then 2 implies, so if b equals to 0, then using condition 2, we know that a sin ka equals to 0, and thus for non-trivial solutions, again, when I say for non-trivial solutions, what would be a trivial solution? A trivial solution is one when psi is 0 everywhere, but that's uninteresting, right? Particle has to exist somewhere, and that's unphysical also. So the trivial solution here is unphysical. So therefore, for non-trivial solution, this a cannot be 0, right? A is not equal to 0. So therefore, sin ka equals to 0, it implies ka equals to n pi, n equals to 1, 2, 3, and so on. Note that n equals to 0 would again lead to a trivial solution, because if n is 0, then like k is 0, 0. So therefore it's again sine 0 is 0. So the entire wave function again goes to 0. So therefore n has to be 1, 2, 3, and so on. So therefore Ka equals to n pi can also be written as 2me by h cut square times a equals to n pi. Right? Why? Because we saw that this is how we defined k. Right? So therefore, what we have is 2me by h cut square a square equals to n square pi square, or therefore e is going to be equal to n square pi square h cut square by 2m a square. So this is something which we obtained, and similarly, like because k is n pi, so k is n pi by a, and therefore the corresponding psi 2 of x is equals to a sine n pi by a. Right? Just to like just from the condition that the probability, like if mod psi square describes the probability, that is equivalent to saying that mod
Sir,
psi
wave
2
function will be a sine n pi x by a, sir.
n pi x by a. Yes, sure. So this is like, say, when we are writing the entire probability distribution, so this should have been the mod psi square thanks for the patience, because I would come to this connection between linear vector spaces and wave functions. So this would be like minus infinity, and then this would be psi 1 square dx plus 0 to a psi 2 square dx plus a to infinity psi square dx. And because this mod psi square dx is 1, because mod psi square probability density. Right, so this implies that because this quantity is anyway 0, and this quantity is anyway 0, because psi 1 and psi 3 are respectively 0 in region 1 and 3 respectively. So therefore this simply implies that 0 to a mod psi 2 square dx equals to 1, and you can check that for the given definition of psi 2 which we obtained, this will imply a equals to root over 2 by a. So therefore we are ending up with this scenario that psi 2x is equals to root 2 by a sine n pi x by a. It's important to note that n goes from 1 to and so on, not from 0. And e, the corresponding e also has a label. So this could be written as n square some e0, right, where e0 is a constant number. I square h cut square by 2m a square. And thus, like typically, this essentially says that the energy is quantized. Right. So energy cannot take continuous values, but it can only for n equals to it would be E0, for n equals to 2 it would be n to 1 it is E0, for n equals to 2 it is 4E0, n equals to 3 it is 9E0, and so on. And similarly, the corresponding wave functions would be root 2 by a sine pi x by a, corresponding to the lowest energy state. It would be root 2 by a sine 2 pi x by a, and so on. So here it makes sense to, let me just add. I think it's already 8:30, so I will take another 5-7 minutes and before wrapping up the class for today. Yeah. So therefore, like it is useful to plot this wave functions corresponding to various n. So for n equals to 1, we can accordingly, so this is 0, this is a, this is x. N equals to 1, the psi 2 was equal to root 2 by a sine pi x by a. Right, and E was equal to pi square h cut square by 2m a square. So in this case, you can see that this wave function would look like, so x equals to 0, this is sine 0 is 0, and x equals to a sine pi is 0. So therefore, this wave function is a quantity like this, and such that if we are labeling psi along this axis, so suppose we say psi along this axis, this is about root 2 by a in magnitude. And now, like what you really see along the x direction are a set of real numbers, right? So, of course, at x equals to a by 2, right, we see a real number which is like corresponding to x equals to a by 2. Psi has a magnitude which is root 2 by a. Psi 2 has a magnitude which is root 2 by a. So therefore, we can also construct, like corresponding to this, we can construct a quantity